Greetings and welcome, friends. Mr. Waddy here. We are talking today about the volume of pyramids. Interesting idea. And check this out. I actually got like this shape here. What type of solid does this shape, the combination of all three of those, look like? A triangular prism. Oh, sure, absolutely. And check this out. I can extrude this green portion off of this, right? Okay, so you guys see that. Those combined volumes are still the same. Would you agree or disagree? Agree. I can extrude the, let's see, oh dear. Is this slider right in the wrong spot? There we go. Right, I can extrude that out. And those combined volumes are still the same. And now, question, they ask, are the red and the blue volumes the same? Man, that's weird that it's like offset. Now, Cavalieri's principle was that if two objects had the same height and equal area cross sections along that height, that they would have the same volumes. Now, gentlemen, these are actually equal area cross sections the entire way. Let's see, can I? They're not arranged exactly the same, but those two figures would be the same volume. And it turns out the same thing is true for the green and the blue. And so either of those pyramids is how much of the volume of the original solid? It is 1/3, right? If they're all the same to each other, they are all going to be 1/3 the volume of the original. No, the original is a triangular prism, which the area of that would be the area of the base multiplied by the height. And it turns out the area of the base multiplied by the height divided by 3 will be the volume for any pyramid, regardless of the shape of its base, which I think is even crazier to me, Isaiah. I don't know if that's crazy to you. But that works for a square base, that works for a hexagonal base. It would work for like a rectangular base. And that's a little bit weird, I think. Non-intuitive in some ways. And it also works for an oblique pyramid. I could tip that pyramid, I could like pick up the vertex and slide it over, and as long as the height stays the same, it will be the same. So now that you know that, we could calculate these volumes pretty easily. So this is a triangular pyramid. So I would find the volume by doing 1/3 the area of the base. This case, the base is a triangle, so that formula is half the base times height, lowercase b, lowercase height, 4 and 6. Multiplied by the height of the pyramid. So I've got multiple heights going on here, I realize. Like so. So let's see. That's going to be, I don't know, how cool are you guys? No, I'll write this out. You guys aren't that cool to do multiple canceling of fractions simultaneously. All right, meh. Let's see. Half of 4 is 2. 2 times 6 is 12. And 1/3 of 9 is 3. And 3 times 12 is 36. So the volume is going to be 36 meters cubed. Right? Whichever way you want to commutative property multiply that, I'm fine with it. Fine with it. All right, so to find the volumes of these pyramids, it's not all that crazy. Let's give ourselves a little bit of work today. Let's do monitoring progress question 2. Isaiah, what is the name of this pyramid, monitoring progress question 2? pyramid, right? Hexagonal pyramid. Now, this is a regular, well, that's actually interesting. It's labeled as an equilateral hexagon, but it could be like a rupee from Zelda shape. But I'm going to assume that it's also equiangular, and we'll call that regular. So let's find the area of that base. I'm going to go with regular. So if this is 12... Yeah, we're getting good at this, though, right? Oh, yeah, we are. So here we go. If I want to find this, I need the apothem. Hexagon, the central angle is going to be 60. So 30 is going to be that. Oh, it's a 30, 60, 90. Half of 12 is 6. And the apothem is going to be 6 times the square root of 3. All right? So the area of this base is going to be half the apothem. Actually, I guess I might as well label that purple. The area of the base is going to equal half the apothem times the perimeter, or half the apothem times the side length times the number of sides. Okay, so for the volume, I'm going to do the area of this base, so that's half of the apothem, 6 rad 3. That's a weird 3. There we go. Multiplied by the side length, which is 12. Area of the base, right? Because I've got the volume of a pyramid is 1/3 the capital B multiplied by height. So that's the, what I'm talking about. Multiplied by 12, multiplied by n. The number of sides that has is 6. So this, in parentheses, represents the area of that base, and then multiply by the height. Fortunately, they gave us the height. I don't have to do any Pythagorean theorem, but watch out. Sometimes they be sneaky, right? What if they gave me, like, the slant height there? That'd be sneaky of them. So let's see. Half of 6 is 3. I don't know. I lost motivation there real quick. Let's see. Half of 6 is 3. 3 times this 6 is 18. 18 times 12. Nope. I thought I was going to do it all in my head, but I'm not. That's 216. Square roots of 3 is the area of the base. Multiply that by 20. 216 times 20. 4,000? 320? Square roots of 3 is the volume of this hexagonal pyramid that is also oblique. It's been tipped over, right? It's slanted a little bit. And this would be in centimeters cubed. So that's the exact value. Let's also then get an approximation here. Multiply by the square root of 3, which is about 1.73, but I'll use the calculator's 8 decimal approximation. 7,482.46 centimeters cubed. So there you go. This formula works even in the case of if I was going to do this in meters, I prefer to convert the centimeters to meters first and then do all the calculations. Converting cubic centimeters to cubic meters, you gotta, divide by 100 cubed? I believe? Yeah. Nah, I'll let you guys figure it out later. Man, oh, yikes, keep moving, Mr. Waddy. We're only on example 2. All right. If we knew the weight of the stone per cubic meter, we could actually then figure out how much a whole pyramid weighs. Actually, side note, I was wondering once, as I do, living in New England, there are approximately 250,000 miles of stone wall in New England from the colonial era. 250,000 miles, which is enough if you were to stack those stones in a width and height, or width and length, of about the average width and length of a stone wall, and stacked them 250,000 miles, would reach the moon. So you could actually take the stones from all the colonial era stone walls in New England and reach the moon in a tower that was as wide, roughly, as an average stone wall in New England. Oh yeah, it would be terrible as a tower. But I actually had the question, and maybe someone on the internet can answer this question for me in the comments. I wanted to know who did more work, the Egyptians building a pyramid versus all of the colonial farmers clearing the stones from their fields and making these 250,000 miles of stone wall. Right. I would want to first compare it to like a single pyramid, and then I'd want to like compare it to all of the pyramids in Egypt. Right. And work is going to be calculated in what, joules or whatever, where it's, I don't remember what's that like. Work is force times distance or something. I don't know. But anyways, originally Khafre's pyramid had a height of about 144 meters. Maybe. Actually, on the enrichment activities, there is the idea of a truncated pyramid, and you can calculate those volumes as well. So 144 meters and a volume. Oh, so they gave us the volume in cubic meters. Find the side length of the square base. So I don't know the square base. So it's a side by side. I know the height is 144, and I know that's a terrible pyramid, but you got the idea. So the volume formula is going to be volume is equal to 1/3. The area of the base, right, is going to be, it's the area of a square. So that's going to be side squared multiplied by height, like so. So let's plug in what I know and solve for what I don't. So 2218,800 equals 1/3 times side length squared multiplied by 144. So let's 144 divided by 3. I definitely should know that. It's 48. I did not know it. 2218,800. So what do I do to solve for S? I like it. Man, good old algebra, huh? 2218800 divided by 48. I get 46225 is equal to S squared. What do I do now? Root root. Both sides, don't forget it, plus or minus. Although we won't care for the negative solution anyway. So the side length is the square root of that. And I get, yeah, 215 meters. There you go. What do you know, friends? What do you know? So you can find missing dimensions like so. I'm going to skip example 3. It's same idea. Let's do example 4. Give us some time for some class quest. Oh, the volumes. Okay. Finding the volume of a similar solid. You guys actually already know how to do this. All right, gentlemen, snapperinos. Pyramid A and Pyramid B are similar. Find the volume of Pyramid B. So if I know the volume of this one, let's see, this one is 8 meters high, this one's 6 meters high. What is the scale factor? So K is going to equal 6/8, which is 3/4. So in terms of linear dimensions, the Pyramid B is 3/4 the size linearly of the bigger pyramid, okay? In terms of area, it is going to be 3/4, the book did not ask us this, squared. So it's going to be 9/16 of the area for, say, the area of the base or the area of any of those side triangular faces. And for the ratio of the volumes, 3/4 cubed. Wow. Actually, that's a sad-looking 3. There we go. Wow. Question? Sorry, what? The scale factor. I was using K from our scale factor days of dilations. 3 cubed is 27. 4 cubed is 64. So it is, to calculate volumes, once I know the scale factor, I cube the scale factor in order to figure out that relationship for volumes. So the volume of pyramid B is going to be 27/64ths of this volume, 96. Right, Jack? You with me here? Y'all with me? 96, I feel like that, yeah, that's divisible by 16. Let's see, 96 is divisible by 16 6 times. 64 is divisible by 16 4 times. Oh, I can reduce that further. 2 goes into 4 twice, Jack, and into 6 3 times. So it looks like 81, right? 27 times 3 is 81, all over 2 would be the volume of pyramid B. Volume, please. Here we go, Mr. Waddy. Come on now. So that's going to be what, 40.5 meters cubed. Yeah. Yep. I was not sure if it was going to come out to an exact decimal or whatever. Last example. Here we go. Ooh, I think I remember when I was a kid, I would sometimes draw houses like this, but I don't think many houses have like a like with a pyramid roof. Or do you do like I do like a triangular prism roof. Okay. All right. But it's just weird that this is a pyramid. So guys, here's my claim. I believe that the volume of the composite, the combined solid, will be the volume of the cube, right, plus the volume of the pyramid. Does that make sense? Let's see. Super sad pyramid. And that's going to equal the total. Right? Are you guys buying it? Alright, it's been bought. I will sell you this sad-looking house. Some assembly required. So let's find the area of the base and multiply by the height, and then let's find the area of this base and get 1/3 multiplied by the height, right? So volume of this guy is going to be 6 squared multiplied by the height, which is 6, plus the volume of this, the area of that base also happens to be, right, if this is 6, Aiden Murphy, right, I know you're excited about this. This will also be 6. If this dimension is 6, this will also be 6. And it looks like the height of that is 6. So 1/3 multiplied by 6 squared multiplied by the height, which is 6. So let's see, 6 cubed is 216. All right. Plus 1/3 of 216. You could tag a video of your house drawing techniques in the comments below. So let's see, 1/3 of that, and then plus 216. I get a total volume, by the way, this was like 72 or something like that, of 288 meters cubed. All right, so volume addition postulate also works for pyramids. Thanks for watching, internet friends. I wonder how far that ant would have to go on this composite solid.